Yeah. So what we have seen so far is some fluid properties, and then some flow properties. Now we do see, so we know exactly what is the meaning of flow. Flow means once you give the deformation, this whatever fluid that you have with all the whatever properties it has, it starts deforming, right? The deformation or strain, whatever you say, strain rate, it is moving, okay, depending on, so it may have internal friction if there is a viscosity in it. And then, so it has certain velocity, right? So UVW components. So first of all, to represent mathematically, we have first of all a body of the fluid. We have the spatial and time coordinates. Okay, at every point in the continuum setup. So continuum hypothesis, you can represent spatial variable, spatial uh, spatial coordinates are x, y, z. We use this one in Cartesian coordinates. Time is t. So these velocities, so implies these velocities. For example, UVW, we represent. This is a velocity vector of a particle at x, y, z, and at time t. So how do we represent this one? So this one, we have two descriptions that are available in fluid dynamics. So one is take the particle. Okay. So first, let me write this. How do you describe this mathematically in the Cartesian coordinates setup? So one is the Lagrangian approach. Lagrangian approach. The description basically. Okay. So Lagrangian approach. So other one is Eulerian approach. Are you aware of this? Very simple terms, Lagrangian approach means basically it is depending only on the time. So you are looking at only one particle. Okay. So for example, x, y, z, t. So you look at particle x. So particle means you can represent with x, y, z, t, right? X, y, z. Okay. So particle means observe. You write it. Observe particle moment. Movement in time. So for each particle in your fluid domain, you are just looking at its evolution over time. So here what we do is, so in that sense, so let me finish this Lagrangian thing. So what you have is, you have x, y, z. At this you have a particle. Okay, fluid particle at x, y, z. Okay, implies in the Lagrangian approach. So you have x is x of t, y of t, z of t, with initial data. Okay, with initial data, that means initially at some point, let us say some x naught, x at t equal to 0, let me call this x naught, y naught, z naught. Okay, so this is true for every t greater than 0. At t equal to 0, initial data, that means x of 0, this is equal to x of 0, this is y of 0, this is z of 0. Okay, so you observe it as a simple function of t. So that is what is Lagrangian. Okay, so implies obviously dx by dt, dy by dt. That is rate of change of this spatial. Okay, with respect to time, x variable, y variable, z variable will give you your velocity, right? Velocity components. This is the velocity vector u v w. This is a velocity vector. what do you do in the Eulerian approach? So what you do is you observe only at one point. Okay, so that is say x, y, z, especially at a time t. So you think that x, y, z, t all are independent variables. Okay, so and you try to observe what you want. So you at this point you try to observe its properties like velocity, density, viscosity. Fluid properties you look at only at one place. For example, you're watching the screen. Actually, frames are moving, right? When you look at the screen, no, so TV screen or movie screen. So this is a perfect example where you see this Eulerian approach. You're only watching that full screen, but actually originally that is those screen basically all the frames are moving. Okay, but you're only observing at one place, and you feel you get the information about what is happening. So with time, so that is an example you can think. And so you observe only at one point. Imagine that x, y, z, t are all are independent. So at this point you look at the properties of the fluid. Okay, observe. So at this at x, y, z in time t, at time t. Okay, observe. So or rather you remove it at x, y, z. Observe the fluid properties. And then see when you do this how it goes. So in the Eulerian approach, so if I say the fluid property is like f some function, okay, so f x y z, x y z are anyway independent, right? The Cartesian coordinate system, so x y z, and t is also independent. You think like this. This is the fluid property. Let us say it may be f may be rho, f may be mu, f may be velocities u, v, w. X component, y component, z component of velocity vector. So if you think like this, and where x, y, z, x, y, z, t are independent variables. So what happens here when you do, and these are independent, you know this total derivative of rate of change of this, right? So the change in f is actually dou f by dou x into dx plus dou f by dou y into dy. The total derivative I'm writing, okay? Plus dou f by dou z into dz plus dou f by dou x dou t into dt. This is what you have, right? Now, how do you get? If you want put f as identity, for example, x itself, right? X, can you put x? You don't know. You will not do, right? So f is for example, if you say if you take f as identity. So what is the meaning of identity? Identity map from xyzt to xyzt. Or simply, if you put simply f as x itself, identity you leave it. So simply put x. X is x value. You're trying to change the x value. Okay. You don't do, right. So in this you cannot take. No, these are only fixed thing you are doing. So we don't do it here. So to get this one, dx by dt is basically it's you in fluids. What you do is in the Lagrangian approach you use, and you actually use this UVW as dx by dt, V as dy by dt, W as dz by dt by Lagrange. Okay, so let me use f as u. Okay, so if I take f of x y z t as a fluid property, for example, u of x y z t, then what happens? Du equal to dou u by dou x into dx plus dou u by dou y into dy plus dou u by dou z into dz plus dou u by dou t into dt. So what is that you want now? If you are interested in calculating x component, for example, that is a velocity component, and you want to see rate of change of x component velocity, then you have to divide with du by dt, right? So du by dt, by dt, if you do it, then you get dou u by dou x into dx by dt. Dx by dt already I have u plus from the Lagrangian approach. Okay, so you're actually kind of mixing. Okay, so dou u by dou y into dy by dt is actually v plus dou u by dou z into w plus here it's simply dou u by dou t. So what you are getting here is the total derivative. So the total derivative is rate of change of the velocity component with respect to time, dou u by dou t, plus dot product with u v w. So that's the gradient of u dot product with the vector, velocity vector u v w. Okay, that is actually the total rate of change of time with respect to as you move. So you say that this is the derivative. This left hand side is the total derivative or material derivative. So basically what you are doing is as you move with the fluid, okay, as you move with the fluid particle, so if you are observing that, okay, so that is basically what you are doing. So rate of change of u with respect to spatial as well as, so this is only temporal variation. Okay, x component of the velocity, rate of change of with respect to only time. And this is actually the contribution from the spatial component, the rate of change of u with respect to the spatial change. So this is what is total derivative. This is the material derivative, also called material derivative. This is a Lagrangian approach. You will get this one. So in the derivation of the equations, normally if you are integral form or differential form and you're doing, so if you are using some fixed domain, and so let us say this is a volume v, and v with time, if you do, as time it varies, that is basically kind of Lagrangian. Okay, so Lagrangian, and I'll basically will mix it. So what you have to understand is there is Lagrangian approach. You simply look at the particle, each particle as a function of time. X is a function of time, y is a function of time, z is a function of time, and then just watch it. You see only that particles, each particle. So that is sometimes inconvenient to work with. So that is why this Eulerian approach is very crucial, because you're actually fixing one point at time t and keep on observing at that point. So basically, it's in some sense x, y, z all are depending on x, y, z. Okay, you're only watching at one point, right? X, y, z are independent anyway, and t is also independent. So that you see like that, as four variables are independent. So in the Eulerian approach, you look at only fluid properties. Okay, so this is the fluid property. Fluid property, if you observe, and the rate of change, if you want to study, you will get your, this is the acceleration component, basically what you get here. So if you want a vector, so what is the vector you get? So finally, so d u v z. Similarly, you can get for v and w also, right? Similarly, you get dv by dt, dw by dt. So if you say if q is the acceleration, okay, so this is q is like what do you write? So q is dot v dot w dot. So you can represent vector ddt. Dot means ddt. Okay. So that is actually, so if you write like this, this is equal to, so dou u, this is a vector, full vector component, u U bar is basically UVW. The velocity at a point. Velocity. This is the velocity vector. Okay. This is the velocity vector. Velocity vector at XYZ. That is actually your vectorial form of your velocities in all directions at any fluid particle. So this is actually U bar by dou T. This is a time variation plus gradient of this U bar dot product with U bar. This is how you write, right? So if you want, you can write like this. Okay. So this is the acceleration vector. Any questions here up to here? Hello?
No, sir.
No, sir.
It's fine. Okay, so how do we see that these two approaches are actually same? So what you are given in the Lagrangian, for example, let's say relation between them are equal, make them equivalents. Okay, so equivalence of Lagrangian and Eulerian. Descriptions. So if we actually see this Lagrange to, so first let us see Lagrange to Eulerian. Okay, given that it is Lagrangian, how do you see it? How do you see that it is Eulerian? Lagrangian to Eulerian. So this one, if you see, actually what is given? So x naught, y naught, z naught, right? So let's say some fluid property. Okay, let f of f is the fluid property. Okay, this is the fluid property. So fluid property, when you look at fluid property of in the Lagrangian approach, how do you see this one? So you actually see as this is equal to phi of x. This is f of, what do you write? This is how do you see this? This is your fluid property, f of initial value, right? In the Lagrangian, you generally initial value. Initial value is x naught, y naught, z naught, and then it's from this point x naught, y naught, z naught to there is a t equal to 0, and then for t greater than 0, it is basically that you're just watching it, okay, as a function of t only. So overall, this is the fluid property. Be the fluid property. Okay, so what exactly you have now? So if you observe only x component, y component, z component, each one is like, so x of t, right? So you will write it as x equal to some function, right? Some function, because this is like a full property. So let's look at this x, y, z component, right? X component is also starting from x naught, y naught, z naught to x direction. What is its component? Okay, so this will be x component of basically this f. Okay, this fluid property will become f1 of x naught, y naught, z naught, that is initial, and this is t. And similarly, yz also, y equal to f2 of x naught, y naught, z naught, t, z equal to f3 of x naught, y naught, z naught, comma t. Did you get this point? Okay, these are the xy components of this one, these three. Okay, so xy components of this fluid property implies or the,
Excuse me, sir.
yeah.
Sir, why we make different function for x, y, z and how it will depend on initial points, sir? X naught, y naught, z naught.
Always, no. See, you started with only some fluid particle at x naught, y naught, z naught. Now you are observing in the three-dimensionally, you are looking at that particular particle only. You are not, you forget everything. Only that ball, small ball, dot. The dot is moving. X direction, X component, you have some function. Already, what is that you are observing? You're not observing that point. You're observing some quantity at that point. Basically, think of density at that point. Okay? Density, you will have initially some density will be there at that point, right? At t equal to 0, you have some density. Now, what happens to that particle as it moves? At different times, it will be a different place, right? So as it moves, let us say, let us look at only, it is moving, no? Finally, so you're calculating density at some other point, at later times, at t greater than 0. So that means you also have three components, right? You are in the space only, right? So those three components, I'm writing x, y, z, and that can be different functions. One direction, x direction, it may be varying in a different way. Y direction, it may be varying in a different way. Z direction, it may be varying in a different way. But all our starting point is only x naught, y naught, z naught. Those are the initial values. And only t is varying. So x is function of t, y is y of t, z of t. Okay?
Okay, sir. Thank you, sir.
Yeah. So now, once you get
Sir,
this one, yeah.
sir, so in Lagrangian, first we only take one initial point, and as the time goes, we will only observe that particle how it is changing over the time.
Yes.
So then,
But
what is
it's
the
not just
difference
the
in
point.
Euler
It is not the point you are thinking, no. So you try to look at its
particle?
properties, particle property. You're observing the
Sir,
particle
and in
property over time.
sir,
Yeah.
and in Euler approach, what you're doing?
Euler approach, you don't follow anything. Only observe that point, let the fluid move. When the fluid is moving, it is looking like four-dimensional space like x, y, z, and t. So you are looking at overall the fluid property overall change as it moves.
Okay, sir.
Okay.
So not just one particle.
not just you're not following that particle. Basically, you see as though you are actually a screen, no, a TV screen you are watching. The frames are actually moving. A movie screen, for example, right? So you're only looking at one place, but you're feeling, no. So it is flowing basically. So you're observing, and the fluid properties you are trying to manipulate, and then you get the feeling of what is going on. Okay. So these are the three components. Followed? So these are the three components x, y, z. Okay. So you don't write this as x of t, y of t. That is obvious. Okay. So x, y, z. Now, what is your fluid property? That is same in both Lagrangian this thing, right? So what is your fluid property? Let's look at. Okay. So these three equations you solve. Okay. Solve and solve for x naught, y naught, z naught. Solve for this, the above equations, the above three equations, to get, what do you get actually? So you actually get x naught. X naught, if you get it as some function, let me write it as a new function, some g1 of what do you get in terms of x, y, z and t only, no? So there is no x naught. So x, y, z and t. Similarly, y naught. Let's call this some g2 of x, y, z, t, and z naught is your g3. You call this some g3 x, y, z, t. So these things you go and put it in your fluid property. What is the actual original your fluid property? F equal to f of x naught. X naught place, I'll put g1 of x, y, z, t, comma g2 of x, y, z, t, and then you have a g3 of x, y, z, t. Okay, and t. T is anyway that, right? So this is finally what is this one? This is actually some function of x, y, z, t. Fine. So
Yes, sir.
is the fluid property in Eulerian approach or Eulerian description. Okay. So now we can do the similar thing for Eulerian too. So second one is Eulerian to, how do you see? So Eulerian to Lagrange. So in this approach, what do you do? What is given for you? Let us say some physical quantity, okay, fluid property, okay. So again, same way you look at it. Let f equal to f of x, y, z, t be the fluid property in Eulerian. Okay, so basically once you look at it, it has all the three components, right? You're only observing at x, y, z. So all the three components you can write like, so what do you have? So this is a fluid property in the flow, right? So fluid is moving. Eulerian is basically, you don't look at it without flow. So there is always a flow, okay? Eulerian fluid property, okay? Fluid property in the Eulerian description of fluid flow. Already is happening, okay? So then immediately what will happen? So you have a velocity component. So u equal to, let's call this f1, okay? So x component is velocity component, okay? Implies there is a velocity vector. Flow means velocity vector is there, right? So minimum. So velocity vector implies u is f1 of x, y, z, t. V is f2 of x, y, z, t. W is f3 of x, y, z, t. Let us say, okay? Say. Now what do you do? Now how do you get this initial values at t equal to 0? So you need, so what is this one? But we already know from Lagrangian, somewhere we are using the Lagrangian. Okay, so this u v w, that is actually dx by dt. If you want dx by dt equal to u, right? So which is given as f1 of x, y, z, t. Similarly, dy by dt equal to v, which is equal to f2 of x, y, z, t. dz by dt equal to w. This is given as f3 of x, y, z, t. Okay, so now what is that you have done actually? See, here you are saying this confusion should get cleared always. The Eulerian approach, we're saying x, y, z, t are independent. Okay, they are not actually independent. The way you are doing in the Euler approach, watching only at one point for different times, that makes it to have a 4-dimensional there. Okay, but if you look at as a particle, it is depending on time also. So that velocity, so the Eulerian components are always flow. Only for flow description only we are doing Eulerian thing. So that is the reason you start with only velocities, not what happens to the x component, y component, z component, that you cannot describe, right, in terms of x, y, z, t. So you have only velocities you can do. Okay, so that velocity you already have from the Eulerian description, Lagrange description. These are depending on time. So now you have this dependence on time. Okay, now what happens? You integrate. Okay, so you integrate, you solve these equations. Solve these equations. You solve these equations to get, what do you get if you solve it? You get x equal to, let's solve, when I solve this, what I get is g1 of x, y, z x, y, z, t, right? Comma, some arbitrary constant, right? C1. Some C1 you will get because you are integrating, no? So you'll have some arbitrary constants. So y equal to y of t equal to g2 of x, y, z, t, comma c2. Z of t equal to some g3 of x, y, z, t, comma c3. Okay. So when I solve it, that is what is happening. So, but you have initially at some point, right? C1, C2, C3. Okay. So how do you fix this C1, C2, C3? By taking initial values. What happens to this? By taking the initial values. How do you take the initial values? What are the initial values? X, Y, Z, no? You started with X, Y, Z from Eulerian to Lagrangian. Eulerian is your description. So, what are the things that you have? X equal to, let us say, initially X, Y, Z. Okay, so X, Y, Z, all of them, you call this A, B, C. You call them A. So, this is your initial values, okay, at t equal to 0. So if you use this one as now you have x of t, y of t, z of t, no? At t equal to 0, x, y, z, you put it as a, b, c. Okay. So x is x, y, whatever you have x, y, z, those are all a, b, c. So you go and put it and fix that constants, right? So those constants are also fixed and it's a different function that implies x of t equal to, so or it's the same function, you can write it if you want, g1 of, you call them because at x, y, z are at t equal to 0, it is ABC. You say it is ABC of t. Similarly, y of t. So basically, you fix those constants in the integration by considering x, y, z as ABC. So I am writing finally the same g1, of course, with some constant, different constant. Okay, whatever c1, c2, c3 being fixed here. So x of t is g2 of ABC, comma t. Z of t is also like now you got something like you are watching a particle. Okay, so this is like a Lagrangian. This is the Lagrangian way of looking at it, looking at the flow, looking at the fluid property. Okay, so what is this one? Property F only. Okay, what is the fluid property that you are looking at? F. That F property, x component is this, y component is this, that component is there. As it moves, its starting point is x, y, z. Okay, that is ABC at t equal to 0. These ABC are nothing but your x, y, z. Just for the sake of writing, we are writing. Okay, so as you see, even if you are in the Lagrangian, you can see it as the Eulerian. Even if it is located in the Eulerian, that is basically Lagrangian. So do you understand? There should not be any confusion now. So what you have to understand is Lagrangian approach, you just start with a particle, you observe it over time. So the particle means x, y, z as a function of t. You just look at it, it's derivatives. You just derivatives with respect to t, you will get your velocity, you will get your acceleration and so on. Any other property also, you can get it like that. For example, rho of x of t, y of t, z of t means you simply calculate rho dash into x dash, all those things, particle wise, you have to do it. Eulerian, you observe at one point thinking that, so only at one point you are focusing and the time is also changing. So at every time you are only observing here. So it's like x, y, z are independent and also t is also independent. So there are 4-dimensional kind of thing if you look at it. Total derivative as a calculus point of view. The total change of, so rate of change of rate of change of time. It's not just only with time. So as you move with the velocity is flowing now, though your observation only at one place, the fluid is moving. So you're actually, as though it is like you are moving with the fluid and calculating things as the time change. What is the change of, for example, fluid density, fluid property like density with time, what is happening with the change of spatial thing, what is happening, all those things. That is what you are actually observing. Okay, that together is actually total derivative. So that is called material derivative, total derivative. Okay, so different names will be given in the fluid dynamics context. Material derivative usually. Okay, some people say that because you're moving, because as though you're watching, you're moving with the fluid, no? So as though you are observing like a particle. People say that this is the Lagrangian approach. So it depends. That's an interpretation. So both are same descriptions, but you will have to see. So you try to understand what is this one, what we are doing. And then see, we may use, sometimes we use for the clarity when it is required, which is simpler, Lagrangian. If it is not simpler, so sometimes Eulerian we use. So how do you know that something is Eulerian, something is Lagrangian? So you see it as if it varies, your domain is varying with time. So that is basically Lagrangian. If it is not, it's Eulerian. So this is the way you have to look at it. So when we do, you will see. Okay. So right now, just get clarified with these two approaches, Lagrangian, Eulerian approach. So we can do some problems maybe in the next class. Okay. So this is what. Any questions up to here? So I think let's get clarity here. Any questions, please? Any questions? Hello.
No, sir.
All clear?
No, sir.
Okay. So maybe let me start with one example. So let's see. Simple ODE solve. You know, you have solved some ODEs, PDs, right? ODEs you have solved, right? System of ODEs. Some example. You have done ODE course, right? First order ODEs you solve.
Yes, sir. Yes, sir.
Okay, so we can do this one. So let's see. For a two-dimensional flow, so you have only two components. Okay, for a two-dimensional flow. What is two-dimensional flow? Only you have two components. Velocities at a point in a fluid. In Eulerian coordinates. Are u equal to x plus y plus 2t and v equal to 2y plus t. So find, the question is, find the Lagrange coordinates. As function of initial position x naught, y naught, z naught. We only have x naught, y naught, right? And time t. So what is its value? So what is the solution? What is that you have done Eulerian to Lagrangian in the second part? What is that you have done? U is given like this, V is given like this. So dx by dt, right? So dx by dt equal to x plus y plus 2t. Dy by dt equal to 2y plus t. You solve this and get x of t, y of t for t greater than 0. with x at 0 equal to x naught, y at 0 equal to y naught. That is what is given, right? So if you use this one, you'll be able to fix those arbitrary constants, the integration constants. Then you have it, right?
Yes, sir.
So what is that you get here? So x, y, see, when you are doing this, no, what is, when you solve it, what is that you get? You only you get it as x of t and y of t with some constants in it. X of t comma c1, okay, and y of t comma c2. That is what you will get. Now if you use this one, so constants will be given in terms of x naught, y naught. So you will have x naught, y naught t. X of t will be similarly y of t will be y of t comma c2 becomes y of t comma c2 will become in terms of x naught, y naught. So that is same as x naught, y naught t. Okay, so your job is just to solve these ODEs. So how do you solve these ODEs? One way is, these are simple ODEs, no? So the best way to solve this is you differentiate, you make it, you put this one, you differentiate this one. Let us say this dx square by dt square equal to dx by dt, and this becomes dy by dt. That is already given as 2 into y of t, 2y plus t plus 2, right? So this is the one. So what is y? Y we cannot get it, right? So y is what? So you have not converted it. So how do I do this one? How do I solve this? Dy by dt or dx by, if you do d square y by dt, so this is so how do you solve this one? So the still unknown y is also here, no? It's not decoupled. So this is actually, usually you do, no? You substitute this into this.
Sir, can we put the value of y from the first equation?
Value of y, if you do it, then you still have dy by dt, no?
No, sir, in the first equation, that means dx by dt is equal to x plus y plus 2t. So from there, if you put the value of y in that equation, then
Which
maybe the
equation?
y.
In the second equation?
Second order equation, not no, sir. After the derivative.
Okay. So you put everything. So let us say, yeah, okay. So that we can do that. So ddt of, the first one is ddt of, in the place of y you are putting dx by dt minus x minus 2t. This is what you are saying, right? So 2 times dx by dt minus x minus 2t plus t. Now you have equation. So this will give me x d square x by dt square minus dx by dt minus 2 times minus 2, right? This is just minus 2 equal to 2 times dx by dt minus 2x plus 4t plus t, 5t, total 5t. So that's what you have. So if you write it, d square x by dt square.
Minus 40.
Sir, it's minus 3t, sir. Minus 3.
Where is minus 3t?
Minus 40 plus t equal to minus 3t, sir. When we multiply 2 into minus 2t equal to minus
Oh,
40
minus 40. So
plus.
it's yeah, okay. Right. That's a mistake. Yeah. So it's a minus 4t plus t, right? So minus 3t. So this one, and when you bring it this side, 3 dx by dt, and this plus 2x. So this is your equation. So you have minus 3t plus 2. Done, right? So this is x is unknown. This is like your constant coefficients. E power t type of solution, if you look for it, x of t equal to e power t, e power lambda t. Okay, will give me lambda square minus 3 lambda plus 2 equal to 0. That's a homogeneous one. Non-homogeneous, first I'm trying to get homogeneous solution. You know, right, how to do this one? Do it at home. So you what are the roots here? Lambda equal to 3 plus or minus square root of b square 9 minus 4 8 divided by 2. So you have a 3 by 3 plus or minus 8.
Sir, 2
So
and 1, sir.
2 and 1, right? So this is 2 and 1. So we'll have x h of t is basically c1 e power 2t plus c2 e power t plus some particular solution in it, right? So xp of t. So how do you get the particular solution? You use method of undetermined coefficients or variation of parameters, or if you have something like some ad hoc methods are there, no? So you try to write it like d square, d minus 2 into d minus 3, right? So 1 over d minus 1. Okay, so try to put minus 3t plus 2. So 2 into e power 0t. So 0, if you put it, you will have minus 3. So this component, 2 component you will have. So what about 3t? What you do? You'll have to, so that kind of thing you do, or some other thing. Maybe we'll do that one. Okay, come up with the solution. What is your x of t? Particular solution, you can get it. So I don't do these ad hoc methods, but you'll forget exactly how to do these 3. Okay, so what I do is, so you'll try to multiply some more. You try to annihilate with the lowest differential operator on the right hand side. Make it 0 so that it's homogeneous. So this in that corresponding solution will be this already there. This you remove it, whatever a thing that with constant, that you assume that is your xp, that you substitute and fix those constants. That is called method of undetermined coefficients. Have you done in your course? Hello? Or
Yes,
let me
sir.
write it. What is the particular solution that you get there?
So
Uh,
actually, we have studied how to calculate particular integral, a particular solution. But this time, sir, we forget the method, sir. I forget the
Okay, fine.
actual
Just
method.
go back. Try to come back with the answer. Okay. So this we do. I think we don't have time right now. So this we do, and then so that you have x of t. X of t will be xh plus xh of t plus xp of t. So you'll get a one solution. Once you get this one, you already have y, right?
Yes, sir. Yes, sir.
From the equation. So
Same.
you have already
Same.
y of t. Yeah.
Yes,
So
sir.
that
Yes.
you only have two constants are there, that you fix it with your initial data. So
Yes,
that
sir. Yes.
gives you x of t and as a function of t and x naught t naught alone. Okay, that is the solution. So we'll see maybe next class how it will be. Okay, next week. Or you just complete and come. So we'll see.
Okay, sir.
Okay, so this is basically we go from Eulerian to Lagrangian. So if it is Lagrangian to Eulerian, that is easy, no? So as you see here, so you already given initial at some point, you started, and this if you do, the fluid properties immediately you just solve them and put it back. That's all. That is simple. You don't have to solve any differential equation here. Okay, Lagrange to Eulerian, you are not solving anything. Only linear equations, some equations, non-linear equations you are solving. Okay, linear or non-linear equations you are solving. But Eulerian to Lagrangian, you are actually solving some differential equations because of dx, but t derivative is there. Okay, so see one or two more problems so that you get familiar with this. So try to understand the basic philosophy of these descriptions, both the descriptions, Lagrangian and Eulerian. Actually, x, y, z and t are independent in the Eulerian approach, but physically, it actually at the end it is depending on t, x and y, x, y, z as a component. If you just watch as a particle again, that particular particle, both the descriptions are same. Okay. So have a thought and just look at other resources if you are interested. Just read the books and okay. So let's see if any questions you have up to here.
No, sir. Sir,
Okay,
I will
so
solve.
yeah, try to solve and then understand the description. I will put these two files into your WhatsApp or by email. Okay.
Okay, okay, sir.
So
Okay.
any corrections also. Yeah.
Oh,
Okay.
okay. Thank you. Thank you so
I'm
much, sir.
closing. Yeah. Thank you.
Yes, sir.
Yeah.